Okay, so here we are going to start our Act 2 of our simplex tutorial, which is going to be on this data structure called the dictionary. So what is the dictionary? Well, the dictionary is just a convenient data structure for linear programs, and it's a way to represent solutions. It's a way to capture the problem. It's also a way that you can use to represent the solution. It's actually a very cool thing, and it captures many different aspects about a problem. So what we are going to learn is just dig very shallow into the world of dictionaries. And as we do duality and learn about the dual solution, you can see that there is a lot happening when you look at a dictionary. And this is something that we are going to develop through the course. Today, we are just going to have an introduction to dictionaries. Okay, so where are we so far? Recall that we have the problem in a standard form. In a standard form, you have the problem as follows. Maximize C transpose X, AX less than equal to B, X greater than equal to 0. So this is the form that we will solve. It's very important to note this. And from here, we can start to do the following trick. And this is a key trick where we add a set of extra variables called slack variables. Okay, and this is a very interesting trick in optimization. Whenever you have something that says E less than equal to F, you can always say E plus some slack equals F, okay? And the slack is a positive or non-negative quantity. Okay, let me be precise here, it's non-negative. And this is a standard trick that you can always use. You can always add a slack, convert an inequality into an equality. Therefore, when you have an inequality of the form A transpose X less than equal to B, which is one of the rows of your linear program, you can always say A transpose X plus a slack variable equals B. Okay? And remember, this slack variable has to be greater than equal to 0, or else you change the meaning of your problem. And this is a standard trick. Another thing to note is that the slack variable has to be a fresh variable which did not exist previously in your linear program. It has to be called something different. It cannot have the same name as an existing variable in your linear program. And those are two very important points. Now, if you got those, then you can change your linear program from this form, this is the standard form, to a standard form with slack. What does that mean? You take A times X, which is the main part of your constraints, and you add an extra vector of variables, X slack 1 through X slack M, okay, as many slack variables as the number of rows of A. Once you add these slack variables, you change AX less than equal to B into AX plus a vector of slack variables equals B. Okay? You have X greater than equal to 0. This is from before, just translates over. And you add an extra set of constraints that say X slack is non-negative. That says X slack is greater than equal to 0. Okay? So this is very important. We added slack variables and we have converted some of the inequalities into equalities. Okay, so if we have added slack variables, let's take an example. Okay, so here is the example. We maximize this objective function subject to these constraints, and this is already in standard form. Okay, you can take a second and look at this and verify that this is in standard form. If so, you can now add fresh slack variables, x4, x5, and x6. Originally, these were less than or equal to, and you convert them to equality. So you change every less than or equal to into an equality through the addition of x4, x5, x6, and these are fresh, which means that they did not exist in the original problem and they are being added to the problem. And do not forget to add these inequalities. X4, x5, and x6 are greater than equal to 0. It's very important to add these slack variables, and now your problem is transformed into something that we are ready to solve. Okay? If you are with me so far, then we rewrite this form. So this is from the previous slide. Okay? So this is from the previous slide. We are going to write it in a very special way. Okay? So what we are going to do is take x4, x5, x6 and put them on the left. Okay? Now you take this expression 2x1 plus x2 plus x3 and move this to the right. So you get 5 minus 2x1 minus 3x2 minus x3. Likewise, you do the same for x5, you do the same for x6. Okay? And we draw the straight line, and now we write down the objective. You can write them down below or above, but as a convention, we write them down below. And one more thing we do is we add a constant term 0 to the objective. Okay? And if you're with me so far, all we have done is reformulate the problem. But wait a minute, we have not added x1 greater than equal to 0, x2 greater than equal to 0, x3 greater than equal to 0. Where did these go? Well, we will just keep them in our mind. These are not going to be written down, but they are going to be implicit, which means that every variable that's here has an associated constraint xi greater than equal to 0 that's simply not going to be written down. Okay? This is called a dictionary. So if you've been with me so far, if you've been with me through all the changes we have done to a linear program, we finally get to our destination, which is a dictionary. It's a way of writing down the program. We haven't done anything great so far. We have just written down the linear program in some kind of a notation, in some kind of a data structure, and we have written it down this way. Okay, and this is called a dictionary. But there is a couple of interesting things about a dictionary. Okay, so first notation is we are going to call these variables basic variables. Okay, so these guys are going to be called basic variables, x4, x5, and x6, and collectively they are called the basis set. So in this case, the basis or the basis set is x4, x5, x6. These three variables form the basis. And these variables, x1, x2, and x3, are called non-basic. Okay. And sometimes they are also called independent or co-basic. Okay. So x1, x2, x3 are non-basic. x4, x5, x6 are basic. Whatever you write down here is basic. Whatever you write down here is non-basic. Okay. So that's a dictionary. All right. So if that has sunk in, let's look at the dictionary in matrix form where it's really easy to write. So we say xb. So set of basis variables is xb, xb1, xbm. There are m basic variables where m is the number of rows in A. So if A is a m cross n matrix, then m is the number of basic variables, and xi is the set of non-basic variables, xi1 through xin. Okay, and there are n of these. All right, it starts out in this case that the slack variables end up as basic, and the original problem decision variables end up as independent or non-basic. But that's purely by chance. As we will see through the process of the simplex algorithm, things will start moving around. Basic variables will become non-basic, non-basic variables will become basic, and that's part of the simplex algorithm. But right now, what you have to note is these variables are non-basic, and these variables are basic, and the letter Z is used for objective, okay, which we write as a constant C0 plus bunch of objective coefficients C transpose xi, where xi stands for the vector of non-basic variables. And this is the original problem. B and minus A. Okay? So this is very important. It's very important that you take a little bit of time and actually internalize the structure, because for the next 2 to 3 weeks we are actually going to spend a lot of time staring at these dictionaries. It's very important that we spend the time and learn about dictionaries and try to understand them as fully as we can.